Everyone, Mr. Smith here. In this video lesson, we're going to talk about the physics behind satellites. So it should be pretty fun. Let's get started. So terrible news, this applet that I have linked on your lesson sheet actually doesn't work anymore. So I have a different one loaded up that I'll show you guys. And I'll make sure to link that one on Brightspace so you guys can play around with it too. But Newton kind of had what we call a thought experiment. So this experiment is an experiment that might not be actually practical or even possible to do, but kind of worth considering. And he thought about making a cannon that was large enough and powerful enough that you could launch a projectile from it. And if we, for the problems we did, on a local level, yeah, the Earth is relatively flat, and our projectile problems, you would come down and hit the Earth. And for a small speed from this Newton's cannon would kind of give you the same thing too. But the idea is, if you could have a cannon tall enough and fire a cannon fast enough, would it ever actually come back to the Earth? Like, what would that look like? And I'm going to flip to this applet we have here. Yes, I got it loaded up here. So here is, so we assume we have like a mountain tall enough, and we got a little cannon on top of here. So, and I have the sound effects loaded up here. So let's fire a cannonball at 900 meters per second. So you can see just kind of like, it's almost like typically what we expect for projectile motion. That's with 900 meters per second. So on the scale of the Earth, nothing really crazy is happening here. And obviously at a local level, we don't see anything crazy happening too, just a regular projectile. What if I pump this up? So I think it was set to 3,000 earlier. So I'll just do 3,200. Okay, so now it's actually, this projectile is actually going down the curvature of the Earth. So sorry, any flat earthers out watching this video. The Earth is round, and so that's what we're working with here. But yeah, at 3,200 meters per second, it comes down and still hits the Earth, but like it's actually kind of goes around the curvature of the Earth a little bit. And let's pump it up to something around 5,000. Okay, so even farther. And can we keep going? What about 7,000? So check it out. 7,000. Now you've almost made it like part of the way around the Earth. And if I pump this up to 8,000, hopefully this illustrates what we want. Goes around. Is it going to come back? And it comes back. And you can imagine if nothing was really there to slow it down, and space is not a perfect vacuum, but for the most part it is. And yeah, there would be nothing slowing a projectile down, like orbiting the sun, let's say. That projectile would just actually continue to orbit and orbit and orbit. And it would be called what we call a satellite. So we're looking at the physics behind satellites today, and we're actually concerned with if I want a satellite to be a certain distance above, like say Earth, what kind of speed do I need to give it so that it would kind of orbit in the satellite I want? And for satellites that have a higher orbit, do they need a faster speed or a slower speed? So these are kind of important questions. And so let's go back to our lesson here and continue. We're actually going to get right in. We're going to derive the speed of a satellite. So it's pretty fun. So let's use our starting point as Newton's second law in the context of uniform circular motion. Sum of forces equals mass times centripetal acceleration. So for a satellite orbiting a large body, we're just going to assume that the sum of forces is just one force. There's one force providing the centripetal acceleration, and it's gravity. So I'm going to do G. I'm going to use a big M and a little m over r squared. And so my big M is, I'm going to say mass of planet, sun. It's the big mass. It's what's being orbited, right? Little m is the mass of our satellite. And remember, in Newton's law of gravitation, r is the center to center separation. Don't know why I capitalized that. Separation. So that r, it's not how high the satellite is above, say, the surface of the planet. It's how far that satellite is from the center of what it's orbiting. So we'll need to keep that in mind later. And on the right, we're going to use v squared over r and plug that in. So I'm going to use m for our satellite, and I'm going to use, instead of just v, I'm just going to put v sat, v with the subscript sat for speed of satellite, divided by r. And we can actually do some simplifying. So what's interesting is that for a satellite at some distance away from a planet, the mass of the satellite doesn't matter. So if you want to have a satellite at maybe 10,000 kilometers above like the Earth's surface, you need to give it the same speed, whether it's 1,000 kilograms or 10 kilograms. So that's pretty interesting. And we can see a factor of r divides that on both sides. And what we get is that the speed of the satellite squared is g big M over r. And so if we just take the square root of both sides, we get this cool equation for the speed of a satellite. G big M over r. So this is cool. So if you want to launch a satellite at a certain distance away from a planet, then you can figure that out. All you need is G, which we know, the mass of whatever it's orbiting, which we can figure out, and the r. And so you can find the speed of the satellite. So that's pretty cool. So this is our expression for, want to be clear, this expression here is an expression for the speed of a satellite. Something orbiting something else in uniform circular motion. And so we're just going to play around with that a little bit. So let's look at our solar system data, and we're going to find the orbital speed of Uranus two ways. I feel like there should be some kind of dad joke inserted in there somewhere, but I think I'll just leave it. I guess in a sense that was a dad joke. So let's use our solar system data, and let's find the orbital speed of Uranus two ways. Because guys, Uranus is a satellite. It is orbiting the sun. It is a satellite. And what it's orbiting is, in this case, a star. The moon is a satellite around the Earth. And of course, we have other satellites too, communication satellites, et cetera, et cetera. So let's use our new formula. So the speed of a satellite, root g m over r. So g is g, obviously. 6.67 times 10 to the negative 11. But what are we going to use for m, and what are we going to use for r? So remember, guys, big M is the mass of what is being orbited. So big M is going to be the mass of our sun, 1.99 times 10 to the 30. And I want to double check that. Yes. You teach this course often enough and you have certain things memorized. And R, what's R? So R is the center-to-center separation between these two things. So it's the center-to-center separation between Uranus and the sun. And that is on our solar system data. So I'm going to flip back here. I have this loaded up. So what we're looking for, guys, is the mean radius of orbit. So that's generally how far Uranus is from the sun, 2.87 times 10 to the 12 meters. 2.87 times 10 to the 12. And let's crank that out. And we'll do it a second way. times 1.99 x 30 divided by 2.87 x 12 and root it. All right, so that's pretty fast. 6,800, basically 6,800 meters per second, 6.8 kilometers every second. So let's verify that, and let's use the period. So, and this is a good tie-in too. So we can also get the speed of a satellite this way. If we knew the distance it travels, i.e. the circumference of its orbit, divided by the time it takes to do that orbit, we can figure this out. So here, 2 pi, this is just the radius of orbit, which we've already used. We used it in the previous question, 2.87 times 10 to the 12. And the period, how long it takes Uranus to orbit the sun. So be careful. This table gives you 2 periods. Remember, one is the period of rotation on this axis. One is telling you how long it takes to spin around. The other is telling you how long it takes to revolve. And in this case, it's that second to last column. It takes 2.65 times 10 to the 9 seconds for Uranus to revolve around the sun. And everything in here is meters and seconds, so we're going to get meters per second. So hopefully it works out to something similar. Yep, pretty close. I got 6805, but I mean, for all practical purposes, that's the same value. So pretty cool. So 2 ways to figure out the speed of a satellite. 1, if you know the mass of what it's orbiting, you can figure it out. 2, if you know its period of orbit, you can figure it out too. So that's pretty neat. So one example in the books, just kind of playing around with our new formula, relating it to uniform circular motion. Let's do a second example. So the Hubble Space Telescope follows an essentially circular orbit, and it's at an average altitude of 598 kilometers above the Earth's surface. We're going to determine what speed it needs to maintain this orbit. So this is important. So when people are considering putting a satellite into orbit around the Earth, they have to consider, okay, if I want it to maintain a certain height, they have to get it to a certain speed. So it's a very important question to answer. And so we're going to find what speed is required. So I want to, in this case, do a little diagram just to emphasize something. So in this question here, so this one is not going to be to scale necessarily, but there's my satellite, and my satellite is 598 kilometers above the Earth's surface. But in our satellite equation, right, root of GM over R is the center-to-center separation. So the center-to-center separation in our satellite equation is going to be the altitude of our satellite plus the radius of the Earth. So that's something we need to consider for this problem. So let's just get going, though. We're going to start with our VSAT equation. GM over R. And what is R equal to in this case? I'm actually just going to replace that right now. So M is obviously the mass of the Earth. But for R, I'm going to put in the radius of the Earth plus, I'm going to call that the altitude we have, H. And now we're ready to go because I know G, I know the mass of the Earth, I know the radius of the Earth, and the question gives me the satellite. So we can just plug in our stuff now and solve for V. Conversely, you could use this equation too. If you knew what speed you wanted to give your satellite, you could kind of resolve for H and figure out what height you need to give it above the Earth's surface. So 6.67 times 10 to the -11, 5.98 times 10 to the 24, the radius of the Earth. First time I'm using that today. To look it up. It is the radius of object 6.38 times 10 to the 6 meters. And the altitude, 598 kilometers. If you want to use scientific notation, fine. Or if you just want to do 598,000, that will work too. Let's give this a go. Use a couple steps if you need to. Times 5.98 is 24. Divided by, I'm just going to use brackets so I can do this in one step. Plus 598,000. By all means, do it in a couple steps. That makes you feel comfortable. And I got 7,560 meters per second. So to maintain its orbit, the Hubble Space Telescope actually has to be traveling at about 7.5 kilometers every second, which is very fast. But something to keep in mind is, you don't have to launch something from the Earth's surface with that speed. Like obviously that's a crazy amount of speed. It just means you actually have to provide enough fuel for it to eventually get up to that speed. So yeah, we're not concerned about launching things with that speed from the Earth's surface. We kind of get it up into orbit and then get it to that speed with various propulsion methods. So that was a pretty cool example. But hopefully that example illustrates the kind of difference between R in the formula and the altitude above, in this case, the surface of the Earth. So you can be mindful of that as you're doing other problems. We're now going to talk about geosynchronous satellites. A geosynchronous satellite is when the period of a satellite's orbit is equal to the rotational period of what it is orbiting. So why is it significant? Well, if you were using a weather satellite, let's say you want this weather satellite to, just always be keeping an eye on the weather for, say, southwestern Ontario, which I think is where most of us are from. You would want that satellite to just always be above southwestern Ontario. Or if it was a spy satellite or some defense satellite that you wanted to always be targeting some certain position. There can be a lot of useful applications to making sure that the satellite stays above the spot, stays above the same point above the Earth. And you can do this. So what you want to do is, the Earth is spinning. We'll just use the Earth as an example. The Earth rotates around its axis once per day. So a geosynchronous satellite would orbit the Earth once a day as well. And so if the satellite is going around the Earth once a day, and the Earth is spinning once a day, then by definition, that satellite is always going to be fixed in the same point above the Earth, which is pretty neat. So that's what geosynchronous means. It means the period of a satellite's orbit is the same as the rotational period of what it's orbiting. So for Earth, that's 24 hours. So let's actually figure out, and maybe, I don't think we've launched any satellites around Mars, but maybe we have, and maybe we want to in the future. But let's find what height above the surface of Mars we would need to put a satellite in order to have a geosynchronous orbit with Mars. And again, I'm reminding you, don't confuse the height with the center-to-center separation. So let's do it. So I'm actually going to start off with, because this question, for a geosynchronous satellite, we have information about the period. We want to use the period of Mars' rotation. So just follow on with me here. So we're going to start with V satellite equals GM over R. And I want to turn this into a expression that contains the period for Mars. So we're going to just make a little equation here. So remember, there's two ways to find the speed of a satellite. We did it in our first equation question with Uranus, is that we could use our newly derived formula, but the speed of a satellite is also just distance over time, 2 pi r over t. And I'm actually going to use that here. I'm going to set these two equal. So root of gm over r for a satellite equals 2 pi r over t. And I'm going to rearrange this equation for r. So how do I do that? Because I've got like a gm over r underneath the square root. So I'm going to square both sides. So when I square that side with the square root, I just get gm over r. And on the right-hand side, I'm going to have 4 pi squared r squared over t squared. If I do some just multiplying up, cross multiplying, I get g times m times t squared equals 4 times pi squared, and r times r squared is r cubed. And now you can see I'm going to get an expression for r. If I isolate r, I get g m t squared divided by 4 pi squared. That gives me r cubed. To get r by itself, I'm going to take the third root. So we did a little bit of rearranging formulas there, but check this problem out. So now if say I'm orbiting Mars, now I have an expression where, if I want to have a satellite to have a certain period, I now have an equation that tells me how far from the center of Mars it needs to be. So that's pretty useful, actually. So we know the mass of Mars, and we know the period we want. And so let's calculate r. So I might just add in a little note here. We are looking up the period of rotation for Mars, not the period of revolution, but the period of rotation. The period of revolution is how long it takes Mars to orbit the sun. We want the period it takes Mars to spin around on its axis. That's 8.86 times 10 to the 4 seconds. Just double check that. 8.86 times 10 to the 4. Cursor back. All right, is that longer or shorter than an Earth day? That is a little bit longer than an Earth day. Interesting. All right, so yeah, let's get calculating. So what we're going to do in this case is let's just find that distance r, and then we'll subtract the radius of Mars to find the height we need. So let's get down to business here. Root of 6.67 times 10 to the negative 11. We need the mass of Mars. It's the mass of what we are orbiting. It is 6.37 times 10 to the 23. 6.3, yep. Period, we just discussed, has to match the period of rotation. So 8.86 times 10 to the 4. Don't forget to square it. All divided by 4 pi squared. So let's get this cranked out. 11 times 6.37, power of 23 times 8.86, power of 4 squared, divided by 4, divided by pi squared, and third root it. All right, so I got about 2.04 times 10 to the power of 7. Yep, so got that, and I got that. So that's the same value I got before when I tried this problem before. So we got to keep in mind, that does not answer our question. That tells us how far from the center of Mars we need to be. So to get our height, we need to take this r and we need to subtract the radius of Mars. So 2.04 times 10 to the 7. The radius of Mars, 3.4 times 10 to the 6. So let's quickly do that. X7 minus 3.46. So what you get is you get 17 million, or 1.7. Is it 17 million? Yeah, it's 1.7 times 10 to the 7. So maybe your calculator gave you 17 million meters. This would be equivalent to 17,000 kilometers above the surface of Mars. This is really useful, guys. If you stuck a satellite in orbit that far above the 17,000 kilometers above the surface of Mars, it's going to stay in that same spot. So again, really useful for weather tracking, for spy satellites, all kinds of useful applications. So yeah, that's pretty cool. Let's continue. Actually, I feel like, you know what? For this question here, the Hubble Space Telescope question, there was something itching in my mind, and didn't actually find the orbital period. So I think that was going to motivate our next problem. So just really quickly, we can go back and do this. I think we have the space. So remember, V satellite, we just use another expression for another way to calculate that is by doing 2 pi over t. And you can actually rearrange this for the period by just doing 2 pi r divided by the speed of the satellite. And so let's just finish this off just for the sake of completeness, and I'll be able to sleep tonight. So r. So remember, in this case, r is the center-to-center separation. So we had 6.38 times 10 to the 6 radius of Earth plus the altitude of the satellite, and we found the speed about 7,560 meters per second. So let's bang this out, see what we get. Then we can move on. Plus 598,000 by 760. Just want to double check that. X to the power of 6 plus 598,000 by 760, and then times 2 pi. So I got 5,800 seconds. I wonder what that is in terms of hours. So if you divide that by 3,600, or divide by 60, it's 96 minutes. Divide by 60 again, it's only about 1.6 hours. So it's pretty crazy. So to be at that height, it's got to be motoring pretty fast. And yeah, it goes around the Earth in 1.6 hours. Pretty cool. All right, now we can move on. So something interesting when we're talking about satellites is to tie in apparent weightlessness. So when we stand on the scale, and I mean, sitting in this chair right now, I'm feeling the chair push up on my body. So I'm feeling my weight, right? So when you stand on the scale, you're feeling your weight. And when you're on a scale, all things being kind of equal, you've got, gravity pulling you down, and the scale is pushing you up, that normal force, and you're feeling your weight. That normal force is equal to mg, and that's what the scale gives you. The scale gives you your weight, except it divides by acceleration due to gravity to convert that to a mass. So you can see how much your mass is. Now, consider you're in an elevator, and I think we've all kind of hopefully experienced this in an elevator that's going down. Initially, when that elevator goes down, you kind of feel a little bit weird. You kind of almost feel a little bit lighter. It's because the scale and you initially are accelerating downwards. And that makes the normal force a little bit less than the force of gravity. Because if you're accelerating down, right, that means the net force has to be acting down. And so that means that, your normal Earth weight mg is always mg. But if you want to experience net force down, that means the net force is going to be a bit smaller and you feel a bit lighter. Now, the next jump up from this is when the acceleration is 9.8 meters per second down, which basically means you're in free fall. In the illustration here, maybe you've been on a ride like this. I myself have never. I don't like heights very much. But if you were to sit on a scale on one of these rides, you basically would be in free fall, and you would experience a normal force of 0. Now, we kind of all understand in space, for, if you were in a space station that's going around the Earth, as Newton's canon illustrated, you are constantly in orbit. You're constantly in free fall, going round and around and around a planet. And if you're constantly in free fall, you're going to be experiencing weightlessness, a normal force of 0. And what we would like to talk about is, well, how could we kind of give the appearance of gravity for somebody that's, orbiting a planet in space? Again, an object that's kind of like going around a planet, a satellite, is kind of like in constant free fall. And it's not good to be in free fall for a long period of time. It's not good to have no gravity. Your kind of muscles they atrophy. And yeah, bad stuff happens to your body. So for health and sanity, a space station can rotate to provide artificial gravity. So how does this work? How does rotating make things better? So the key idea is this. So just like centrifugal forces when we are in a turning car, rotating a space station can simulate gravity. So if you rotate a space station, so say you're floating in a space station and it's kind of cylindrical like this. If you rotate the space station, you're going to kind of want to continue in your straight line of motion, and you're going to press up against the side of the wall, the space station. And that wall is going to exert a force on you, the normal force. Well, if that wall is exerting a normal force on you, that can kind of give the appearance that you actually have some weight. And you can kind of simulate artificial gravity. And so if you can rotate the space station fast enough, you can actually simulate Earth weight. So we're going to do an example. We're going to find how fast we have to rotate a space station in order to provide a normal Earth weight to an astronaut. So keep in mind, this space station we're looking at has a radius of 1 kilometer. So much bigger to scale than what we're considering here. But this is kind of like the scale of problem we would need to consider if we were going to transport people a long distance in space. Obviously, we would have pretty large structures, and we would want to provide artificial weight. And so, yeah, they're going to be pretty big. So what speed would we need to rotate this outer point at, and what is the period of rotation? So let's continue. So if we set up Newton's second law in the context of uniform circular motion, what's providing the centripetal force for our astronaut in our space station rotating around? Well, remember, we're in space, so we're far away from any big body, so the gravitational forces are negligible. The only force acting on this person is the contact force between the outside and him or her. And so the centripetal force here is the normal force. M, and I'm going to write MAC as mv squared over r, because the first thing we're kind of going to try to find is how fast we have to have that outside point be rotating. Now, to simulate Earth weight, we want Fn to be mg. That is just like normal Earth weight. That's what we want. We want them to kind of feel normal. So mg equals mv squared over r. And so we can see it doesn't actually matter how big or small the person is. If we want to simulate Earth gravity, then we need to make sure that they're moving at, so if we multiply up the r, we get gr, and we will have to square root. So the root of gr, which is easy to calculate. So for us, normal Earth weight, we would want g to be 9.8. And the radius of our space station is 1,000, or 1 kilometer, or 1,000 meters. Let's see what we get. So that'd be the root of 9,800. So yeah, 99 meters per second. Now, that's how fast that outside of the space station has to be rotating. That doesn't give you, like, for me, I have a hard time visualizing how fast that would have to be turning then. In this case, the period, I think, actually gives you a better visual of that. So the period, remember, VSAT is 2 pi over t. So T is 2 pi r over V. 2 times pi, r is 1,000. And we just found V to be about 99 meters per second. So let's calculate this. So it would be 2,000 times pi divided by 99. It's about 63 seconds. So the space station needs to rotate once every 63 seconds. So once every minute. So I can get a bigger idea in my mind of what that looks like. Now, we're going to pause there, but there's actually like a lot of interesting things to think about here. So that is obviously a massive structure. What kind of structural forces is that going to, like, in stress, will rotating this huge structure once every minute put on it? It could be quite significant. So you'd have to make sure your space station can handle rotating that fast. It might not seem fast, but for a massive object, 1 kilometer in radius, that could be quite a bit. Other problems rise up too when talking about artificial gravity. One is called the Coriolis Effect. Now, right now, this is just interesting. I'm not going to be testing you guys on the Coriolis Effect, but it's just a kind of a complication. What happened, if you can imagine? So let's say you were an astronaut in the center of your rotating spaceship. So you're in the center, right? But your friend is on the astronaut on the outer edge. So if you kind of try to pass a ball to your friend while they're at this point here, well, when you pass the ball, it's going to travel through the air, right? And your friend is going to rotate past it. So what you're going to kind of see, because you're kind of spinning around and you always see your friend in front of you. So what you're going to kind of see is that the ball curves through space. Now, this doesn't violate any laws of physics. This is because you're in a non-inertial reference frame. You're in an accelerating reference frame. So kind of weird things happen. So this is called the Coriolis Effect. By rotating your space station, you might, at the edge, have your normal Earth rate, but it doesn't mean things will be normal. You'll have things like the Coriolis Effect happening. So if you were to drop an object, it would actually kind of float past you or in front of you and curve away from you. Weird things happen. So that's just one complication. So if you'd like, and this is not mandatory viewing, but when I'm teaching this course face to face, I always find it interesting to watch with the group. This is about a 10-minute video from PBS Spacetime. It's definitely worth a subscribe. There's a lot of interesting physics stuff from these guys. But this video actually looks at, which video game or TV show or movie kind of tackles the idea of artificial gravity and kind of in a most realistic way. So it's pretty cool, worth a watch. Check it out. Definitely worth a subscribe to. They're not paying me. It's just, you should subscribe. It's pretty interesting stuff. All right, guys. I really enjoyed that lesson. It's one of my favorites to teach. Up next, we apply the physics of satellites to the planets and other orbiting bodies when we look at Kepler's 3 laws of planetary motion. So I can tell you that lesson won't be too long, and it's pretty light on the math. So it's interesting, but it should be pretty light. Looking forward to teaching it. That's it for now, guys. Hope you're staying well. Have a great day, and we'll see you soon.